to start the recording.
Okay.
Yeah, and then I can, once I just give you this example, I'm going to just cover an example on deflection in curved beams, and then you can just stop me anytime, ask questions, and then if you have any additional questions, we can go through that.
Okay.
All right. So the deflection of curved beams is a little bit different from straight beams because at every point, even if you apply a force anywhere, you get a bending moment and you get a shear force. So if you have a curved member like this, then you apply a force on one end here, and then you take a section. And in this section, at an angle theta, you transfer this force to the centroid of that section, or to the neutral axis. So this force, when it's translated here, it comes with a moment from statics. So the moment is basically the force times the distance, which is r like this. The force here times the vertical distance, and the vertical distance is r sine theta. So we have a moment, and then we have the force. And the force, we can decompose it into a radial component and an azimuthal component. So from a simple force here, we get a force system, one radial, one azimuthal, and we get also a moment. And then the curved member will store this elastic energy. It will actually look like a spring, and you're storing the elastic energy in this spring. So if we go to, now we're trying to compute the contributions of this force system to the storage. We have an energy due to the moment, which is m squared over 2aE, and then you divide by the elastic modulus E, and you integrate over theta. So if you go back to the lectures, we used to have an r d theta, where it's a line integral, and there's an r downstairs here that canceled out, so we have m squared d theta over 2aE times elastic modulus. And E is the eccentricity, the difference between the centroidal radius and the neutral axis. So we have to do a little computation for the neutral axis. So this is one component. So, and then we have to get another component for the azimuthal force, and then one component for the radial force. The azimuthal force is axial, so it will be F squared over 2A times E, which is elastic modulus. And then we have to integrate this over the length. The radial force is shear, so it will be F squared over 2J over 2G, or 2 times the area times G, and then integrated. So you have these three components. This is a component for the axial force, an integrated RD theta, and a component for now the axial force. The only thing is that the axial force is not applied to a straight member, so it's applied to a curved member. So you have to recover part of the energy, because the axial force it also causes a bending moment on its own. So there will be, the axial force has two parts. One part is F squared over 2aE times the length, which is what we know from a straight bar, minus the effect of the influence of the axial force on bending, which is m times F over AE. So these two contributions have to be together. And then the last contribution is the shear. So you have the shear contribution here, and the shear, instead of the elastic modulus, we have the shear modulus downstairs. So in summary, it's a bookkeeping process that you have the elastic energy as these four contributions. And Castagliano's theorem is that the deflection in the direction of an applied force. So if I have an applied force F and I want to find the corresponding deflection, then I find the derivative of the elastic energy with respect to the force. So it's very important to know that we can take the derivative with respect to the applied force. And if you look upstairs here, all of the terms have the force and have some relationship to the force. So the relationship to the needed force comes into the m and the f theta and the fr. Therefore, when we take the derivative with respect to a desired force, so F is a desired force, then we just ignore everything else except for the loading components, the M and the F theta and the FR, and we take the derivative of those with respect to the desired force. So that's kind of the general formulation. Now, in practice, if we have a member that has the radius of curvature much larger than the beam depth. So if R over the thickness is greater than 10, then all of these contributions become insignificant except for the first one. So most of the elastic energy gets stored in bending, and that makes it very simplified. So if we have members that look like wires, for example, where the radius of the wire is small compared to its radius of curvature, then we can readily remove all of the last three components and just retain the first one. So the example that I wanted to give is exactly on this. So here, this example, we have basically a wire that is curved like here. It has a straight section AB, and it has a curved section BCD. And then we're applying a force in the center. And the question that we wanted to answer is, what is the deflection of the tip D to the forces applied here at C? So the deflection, the desired deflection, is at a location where we don't have a force. And from Castagliano's theorem, we need to take the derivative of the energy with respect to a force that is applied at a point where we desire to find the deflection. So the idea here is that if we need the deflection under the force P, then we write the energy for the section AB, BC, and CD. We add them up, all of the energies, and then we take the derivative with respect to P, because we want the deflection along the direction of the force P. However, we don't want this. We want the deflection at the tip, D, where there's no force. So what we do is we introduce a fictitious force, Q, that we think is extremely small. We do all the math with this for this applied force Q plus the P. And then when we do the integrals, we set Q equals 0 inside the integrals and find the deflection. So that's the idea. So let's go through that. Here's the sections. We have section AB, CD, BC, CD. So there's basically three parts that we need to compute the elastic energy for each part and then add up the three parts. And the computation involves a Q and a P, and it's all moments. So if we take a section AB, then we need to have a coordinate to do the integration. And the coordinate, we can take X from this side here, or we can take X from the origin, from A to B, for example. We can take X going this way, or we can take X going from B to A. So it depends on which one would make life easier. Well, if we take it from B to A, it might be a little bit easier because all distances away from the force P or Q will basically be a radius plus the X. Otherwise, if we take it from A to B, it will be the radius plus L minus X. So let's take it from B to A. And therefore, this section here, we would have the energy. We have to compute the energy in a straight section. And then we go from BCC to C. We compute the energy in a curved section. And then finally, from C to D, we compute the energy in that curved section. So it's 3 parts. The straight section is the moment here. So if we take a cut, the cut will have a moment to equilibrate the left face of the section, and the shear force also needed for equilibrium. So since we decided that shear is not going to add much to the elastic energy, then we just keep the moment. And the moment MAB is balancing P times the distance, which is R plus X, and balancing also Q times the distance, which is 2R plus X. So very simple. And this is the moment here in equation 1. And then before we enter into the integrations, we need not only the moment, but we need the derivative of the moment with respect to the point, to the force at the desired point. And the force at the desired point is Q. So we take the derivative with respect to Q, and that gives us 2R plus X. If we go back to the equation for the delta AB due to AB, so the delta at D due to the energy stored in AB. That's the way we read it. Delta at point D due to the energy stored in the section AB. And that is 1 over EI times M dm by dq. So when we do this, we need M, which is this long expression, and then we need dm by dq. And when we introduce the 2 parts, we get x squared. So we get some kind of quadratic here that has an x squared. And then we integrate from x equals 0 all the way to x equals L, the length of the straight section, and get the deflection at point D due to the elastic energy stored in the straight section. So that's for the straight section. For the curved section here, we have to start from the free body diagram. In the free body diagram, we should take a cut, and the cut we equilibrate on the left side of the cut, all of the forces and the moments on the right side. So at that cut, I have to introduce a shear force VBC and a normal force to the face, NBC. And then in addition to that, I introduce the moment at BC. Again, the contribution to energy due to, in the shear and the normal will be ignored because it's a very thin wire, and then we just keep the moment. And the moment here has 2 parts, P times that distance. This distance is R sine theta, and then plus Q times this long distance, which is R plus R sine theta. So you get these 2 parts, and you take the derivative with respect to Q, and again, we put it back into the M dm by dq formula, divide by EI, and integrate now over theta, not over X. So the book has an error. This should be d theta here. So when we do the integration, in these kinds of problems, usually we end up with a sine squared or cosine squared because of the product. Like if you go back to the straight section, because of the product, you end up with a quadratic somehow. And for the curved sections, you would end up with either sine squared or cosine squared. So we would need to know the integration from 0 to some limit, like pi over 2 in this case, of a sine squared function. And usually we can convert it to the 2 theta formula, and then we do the integration. So if we have like access to an integration book, we could use it. Else, if it is on a test, then we would get the form of the integration. So once we put it here, we get 1 plus pi over 4 multiplied by PR cubed over EI. And then finally, the last section here, we would see when we break it and find the equilibration on that side, the moment is balancing only Q, and then the moment will only have a Q, and when you take the m by dq, then you will have a Q also so in the product it will have a Q, and since Q equals 0, then there will be no contribution to the elastic energy from that section, because Q is really a fictitious force and it doesn't store any energy here. So it turned out to be that in this section we have 0 contribution to the energy, and only we have this delta due to AB and delta due to BC, and adding up, then we can get the final result. So that's the example that I wanted to cover, because it has some relationship to the homework assignments, and also a lot of times we have this on exams and so forth. So is there any, do you have any questions on this example?
I think I'm okay, actually. That was pretty good.
Okay. Yeah, so this is kind of a nice example that shows the curved sections. In the worst case scenario of these types of examples, then we actually have to kind of bite the bullet and then use this long form. For example, if you have, this is a long form that combines the 4 terms in the energy. So it becomes kind of a tedious process, but it's essentially the same idea, that you either have an actual force F or a fictitious force Q, and you take the derivative with respect to either F or Q, depending on where you want to find the deflection. So now I have actually another comment that comes to mind, is that suppose now that you want to find the deflection. You see, like this point D here is, we wanted to find the deflection. D, when you put force P, then this node D is going to move both downward and is going to move either sideways, somehow sideways, right? It's like, it's going to, like the point D will, you know, if you push here, then this D is going to come down, and then also will come some angle, like another direction in the horizontal direction. So suppose that I want to compute the deflection of D horizontally. Where is it going to be? Where is D going to go on the horizontal axis? What should I do in this case?
Let's maybe do like a free body diagram of kind of the point D and analyze the theta, and maybe assume that it might go towards the left hand side once you pull that, since it's rigidly fixed at A.
Yeah, so it's the same idea here.
And then maybe U forces.
Yeah. Yeah, so that's okay. So this will be an interesting case. Like you said, we will follow the same idea, the free body diagrams in section A, B, and C, D, and so forth. But the placement of the fictitious force Q, instead of placing it to go downward, we place it to go horizontal. So we would have a horizontal Q at this edge, and then do exactly the same thing we did, but with a horizontal Q. Then in this case, the answer that we will get will be the motion, the delta at the tip D, due to horizontal fictitious force, because the deflection is computed in the direction of the force. So here we have decided that the force direction is going to be horizontal, and that can give us a deflection in the horizontal direction. So, you know, to summarize, if I want the deflection downward, then I can put a downward force Q1. If I want to find the deflection horizontally, I put a force Q2. and I do the same thing, the answer will be different for Q1, different from Q2. Now, if somebody asks me, what is the resultant direction, what is the angle of the deflection at point D, then I have to find deflection due to Q1, and then due to Q2, and then I have two deflections. So it will be one horizontal, one vertical, and then I can sum them up like a vector and a vector diagram, and it gives me the exact direction of the point D. Where is it going to go, and also in what direction. So this is a very nice feature of Castagliano's theorem. Okay. Any other questions, Anthony?
Cool.
Yeah, I think I have a hard time hearing. Maybe my my network is kind of unstable.
Oh, sorry. Yeah, it might be my internet too. I said, yeah. I think everything was pretty clear. Yeah, I think that was a good example.
Yeah. Okay. Yeah, I'll post it on the on our website as well.
Okay.
Yeah, go ahead.
Oh no, yeah, I was just agreeing with you.
Yeah. Okay. How is the project going, by the way?
So far it's going okay. I've been getting I got my von Mises stresses, and I think I'm headed towards like completing like the buckling portion of it.